panel from really diverse backgrounds. For example, today we have Gokul and we are trying to look at a mechanical engineering project. But we have dealt with everything from radio astronomy to data-driven astrophysics to sustainability related problems, right? We've looked at climate tech, we've looked at understanding how CO2 data can give us some really valuable insights. And we've also done some quantum computing courses. So we're really interested in science and technology as a whole. But there's one pattern about the kind of programs we do, that is, we really believe in project-driven learning, which I think is quite apparent if you look at the kind of programs we offer. So we really think anything that is taught in the process of solving a problem or in building a project, you really grasp the ideas a lot better and you get to learn a lot more as a byproduct of solving the problem. So that is exactly what this project is about. And you can see the topic here, the dynamics of IC engines. And Gokul here today will obviously delve into it a little bit more deeper. But I just wanted to say we are starting this project in roughly 10 days. So today's discussion is for you to check out what this is about. And if you have questions, please do feel free to interact. Maybe Gokul, you can give a couple of minutes break after say 15 or 20 minutes for people to ask questions if they have. So throughout the conversation, you can also put your thoughts on the chat box and we will address it soon. So I would just like to quickly thank Gokul for being here and I'll quickly introduce him. So Gokul is currently a research scholar in the Department of Physics at BITS Pilani. He's working on an interdisciplinary project. He has an undergraduate degree in mechanical engineering and worked in SAIPEM as a design engineer before graduating with a Master of Science in Physics. He has teaching and research experience in mechanical engineering, theoretical physics, and applied mathematics. You will, of course, soon realize that all the things he's worked on are really interdisciplinary in nature, in the sense that he brings together his interest in both engineering and physics. And that's precisely why we think this is there's an interesting interface to explore. So again, welcome all of you to the Nakshatra community, and let's get the discussion started. Thank you. Gokul, if you are here, you can get started. Just one last thing. Sagar here, who's our team lead, will be posting a couple of links on the chat box. If you're interested in, if you have not joined any of our discussion forums yet or the WhatsApp group, please do. Secondly, if you want to explore the project page a little bit more in detail, we will share that as well. Thank you.
Am I audible?
Yes, Gokul, yeah.
Lovely, okay. Very good evening to all. Thank you, Sitara, for this wonderful introduction. I don't think I could have done it better myself. And thank you guys for joining on a Sunday evening. I can understand, I mean, it's really moving that many people are turning up for a meeting, informal as it is, but on a Sunday evening. So thank you for joining. And I think Sagar has done the needful in the chat box. So he's given you some links. Please check them out. And if you're interested, please do register for this course. And as Sitara has said, it will be starting in around a week or 10 days. So today's discussion will be quite an informal one. And I will be using many things to, basically drive a point. And you'll see that shortly. And I believe the meeting is scheduled, at least it has been set for an hour and a half. So I hope I can give you something at the end of 90 minutes, like a football match. So please stay tuned. And of course, as is always the case, you may raise your hands or you can unmute and ask questions if at all you have any questions in between. So without further ado, let's get started. All right. Let me just share my screen. All right. Yeah, is the screen visible?
Yes, Gokul, it is visible.
Lovely, lovely, lovely. No worries. Let me just start my presentation. Yeah. All right. Good. Okay. So, the whole idea of this project, as Sitara has said already, is trying to bring the best out of physics, mechanical engineering, methods of applied mathematics, and stuff together. And the whole idea is to give you a taste of what mathematical modeling is all about. And I hope this project will really be helpful to people who would like to explore ideas in mathematical modeling. Particularly, this project would be suitable for people with interest in modeling complex engineering problems mathematically. So I have gone to SlideShare. Why is it not showing up? Okay, just a minute. I have 1 second. All right. So okay. So it is. I have gone to SlideShare. It looks like it's not coming. 1 second. Okay, just give me a minute. Yeah, all right, lovely. Okay, is it visible now?
Yes, it is
Perfect,
visible.
perfect, lovely. All right then. Yeah, so the whole idea is to give you a taste of what mathematical modeling of complex systems is all about. And being a mechanical engineer and who's extensively taught these subjects to undergraduate students and graduate students at that at different universities, I believe that this is probably one of the strong points that I have. And I don't think a system is more beautiful than studying IC engine. IC is basically IC stands for internal combustion engine. And the reason is, of course, I mean, you'll explore those reasons as to why I had taken this particular engineering problem in the slides to come, and whatever I'm going to discuss for the next 90 minutes. So yeah, let's start our presentation. Yeah, all right. Okay, so what I hope to answer before I complete my presentation is a few questions. So the few questions are: what is mathematical modeling to start with, for people who are not aware of what it is? And then what is an internal combustion engine, and why model internal combustion engines mathematically? And a more pertinent question would be: will internal combustion engines stay relevant in an age where electric cars become the norm? I mean, what's the whole point of doing this project? And how is this project structured, and what you guys will learn? And finally, of course, which is the crux of today's presentation, is what is the problem briefly, and would I be a right fit for this? All right, so let's start with mathematical modeling 101. So mathematical modeling, as this is the sort of a textbook definition that I just manufactured a couple of hours ago. So mathematical modeling is the process of developing or deriving mathematical equations that describe the working of a complex system based on reasonable assumptions. So as you can see, I've put an asterisk on reasonable assumptions. So reasonable assumptions means different to a different means differently to different people. So for a physicist, not so much for an engineer. So I hope you guys understand, right? So it depends on who is trying to mathematically analyze a problem. So you have three people who try to model problems mathematically. Actually, four people. But then you can sort of club the fourth group of people into into mathematicians themselves. So engineers are people who do mathematical modeling. Physicists are obviously the other theoretical physicists at that. They are that's their day-to-day job. And mathematicians, particularly applied mathematicians and economists, will be mathematically modeling complex systems. So so engineers, physicists, and mathematicians model. So when I use the word model, it basically means we try to solve a problem. And quite an interesting thing about this is that these three different people solve the same problem quite differently. So it's not a joke that I'm trying to put forth. You might have read jokes like, what is the difference between an engineer and a physicist and a mathematician or something like that. So it's not quite the same. So this is they approach the exact same problem in three different ways. And I hope to explore some examples through this, but I'll get to these examples towards the end of the presentation, because that is where things really get a lot more enriching knowledge wise. So let's explore the examples towards the end. But I just wanted to start off with a definition what mathematical modeling is all about. And I hope I've answered what the first question is all about. And of course, through the examples, I'll be illustrating towards the end of the presentation as to what I really mean. So coming to the second slide. So what is an internal combustion engine? And there are three questions that pop up. Those are: what is an internal combustion engine? Why am I going to study internal combustion engines, and what is so special about that? And how do I study internal combustion engines, and how do I mathematically model? So in the subsequent slides, I hope to answer these questions. So what is an internal combustion engine? IC engine is essentially a machine that converts chemical energy liberated by combusting air fuel mixture to do some mechanical work. And that mechanical work is performed by the expanding hot gases. So I've also given a small picture here. I hope you guys can see that. So the internal combustion engine, as you can see, that I've shown in the slide, is that of a four-stroke engine. A four-stroke engine is essentially an engine where am I audible? Hello? Sorry. Am I audible?
Yes.
All right. Sorry. Apologies. All right. Sorry. Yeah. So a four-stroke engine is essentially an engine where you have four different strokes. Four different strokes in the sense you see the. All right. Let me start using my pen here so that I can drive a point. Yeah. So four strokes, as you can see, this one. Can you see my pointer? Yeah, I think you can see that. Right, lovely. So you can see that there are a few components to a four-stroke engine, particularly an IC engine. We'll get to the nomenclature and other things in the subsequent slides if need be. But the whole idea is that four-stroke engine is an engine that has four strokes, as the name suggests. And a stroke is basically a 360 rotation of this particular thing. So you see that this is going to rotate, and this is going to rotate for 360 into 4. And for each of these strokes, you have some interesting thing happening. So while I don't think this is exactly relevant to the problem of investigation here, but I thought, just trying to drive this point across will enable you guys to check on what a four-stroke engine is all about. So you have four different strokes in a four-stroke engine. The first stroke is basically the inlet stroke, and it is basically when it is when the piston moves down for the first time. And when the piston moves down for the first time, you see that there is a vacuum created, and one of the valves is actually open. That is going to be your intake valve, and air from the atmosphere will obviously occupy the space, as is always the case. So air occupies the space, and that is the inlet stroke. So the inlet stroke, the intake stroke is basically trying to draw the air fuel mixture inside. So that is done. And the second stroke is compression. So you have two different types of igniting your air fuel mixture. So one is compression ignition, which is the point that we'll discuss in detail in our problem. Compression ignition is what happens in a diesel engine. And you have another type of ignition called spark ignition. And what I've shown here is essentially the spark ignition. So you have a component here called the spark plug. So the spark plug is going to ignite the air fuel mixture at the end of the compression stroke. So that is when you have the power stroke. So in the power stroke, as you can see, the air fuel mixture after getting compressed is being ignited, and the hot gases are expanding, and they are driving the piston downwards. So in four strokes, you see that there is just one stroke that is giving you power. The other strokes are just trying to set up for that one stroke. And of course, the last stroke is the exhaust thing, isn't it? I mean, you don't want the air fuel, the combusted material within your engine, and they're going to get exhausted, and that is what happens. Is this clear? Do you understand the simple working of a four-stroke engine and what these strokes actually mean? Can I go
Yes,
ahead?
Gokul. Yes,
right.
but there is one doubt. Isn't
Please.
like one stroke 180 degrees as said by Abhik Mishra?
1 second, let me just check. All right. So it's actually 360, but no worries. So yeah, actually, so I'm sorry, apologies. I think it is 180 because Yes, 180 degrees because I mean, we'll get to why it is 180 degrees in the future slide. But the idea is the maximum extension of your piston is going to be like this. So if this is your stroke, just so the maximum extension of your piston will be when this is aligned in a straight line. So it will be like this. And the retraction will essentially be when it is like this. So the angle is is 180 degrees. Yes, so 720 degrees. I'm sorry, I stand corrected. My apology. So 720 degrees is all it takes for one power stroke to happen, and 720 is, I think, 18 fours are 72, isn't it? Yes. So that makes sense. All right. So is this clear? Can I go ahead?
Yes, yes.
Yeah,
All
I didn't get how 720 again.
all right. Okay. Let me just repeat that. No worries, please. Thanks for asking these questions. I hope you can see the annotations that I'm making here. No worries. Let me just draw this. So let's say I'll be covering this in a future slide, but nevertheless, I can. It is always doable.
Sir,
Yeah.
the distance taken to reach the power stroke, is it exactly 270 or is it between 270 and 360?
Okay. So these are some. Obviously, it cannot exactly be 270 degrees because it will be around 270 degrees, around 270 degrees to 360 degrees, and there is a very good reason why. So those are some technical details which will be answered when I'm trying to holistically explain to you guys what the engine is all about. So, but I mean, at least for for the time being, you can say that it is going to be around 270 degrees. So the third stroke is of yeah, the third stroke is like 1 second. It's not 270. I'm sorry. What is it? It's 180. Yeah, 180. So yeah. Who was the 720-degree thing? Yeah. Okay. So this is your piston head, and this is your crankshaft, and this is your crankshaft. This is your connecting rod. Okay. So this is your connecting rod. This is your crankshaft. Crankshaft is going to rotate. That is going, and this is arrested to only have translational motion, which means it is only capable of. I mean, it only has 1 degree of motion, and this has 1 degree of motion in the sense that it is going to rotate. Right now, as the crankshaft rotates, and you see that this is the position of your crankshaft. So what do you think is going to happen to the connecting rod? The connecting rod will have to be like this. Yes, and it is going to. This will be the. Let's say this is the first stroke, and in the inlet stroke, as you can understand, or the intake stroke, you see that the piston is retracted almost completely. Of course, they've shown it being as a part of the intake stroke, but the intake stroke is essentially completed when this guy and these two guys are like. So you see that. So I hope you can understand, right? So this gets completely retracted here, and you have the connecting rod here, and you have the crankshaft here. Maybe I'll make use of a different color. So this is your connecting rod, and this is your crankshaft. So this is the completion of your intake or your inlet stroke, intake stroke. So let's say this is where your angle actually starts off, because it's the very first stroke, and then in the next stroke you have a compression, which basically means that this guy will have to come all the way to this side, and which means your crankshaft is going to be, I'm sorry, change the color, which means your crankshaft has come here, and your connecting rod is going to extend maximum possible way. So this is what we call what we engineers call as stroke. So stroke length is basically the maximum length that can be traversed by your piston head. So in the first stroke, which is your intake stroke, or intake stroke, you have your crankshaft and connecting rod in this fashion, and then your crankshaft starts to rotate this way, it comes here, and the connecting rod, which is a rigid member connected to your crankshaft, will extend by this amount. And basically, your cylinder is going to oscillate back and forth within these 2 points. And this is what we engineers call as stroke length or stroke. Is this clear? Hello?
Yes, sir.
All right. So this is called stroke. So what do you think is the angle that this crankshaft has made from this point all the way to this point? It has rotated by?
So 2 rotations.
No. I mean, I'm talking about this stroke to this stroke. So intake stroke has happened and the crankshaft has completed some rotation and it has ended up in this point. So what is the angle it has swept on your circle?
270.
Anti-clockwise is positive. Okay. So it has gone from this place to this place. So what is this angle? Is it 270? Are you able to follow?
Yes.
It has rotated this way. So how is it 270? What is the angle? It's 180, isn't it? This is 0 degree. This is 180 degree, isn't it? Anti-clockwise is positive. This is it would have split from 45 degree, 90 degree, 120 degree, all the way to 180 degrees. Is this clear? Please, guys, you can unmute and tell, because I can't really look at the chat at all times. No worries. Yeah. Okay. It's clear. Lovely. So 180 degrees. Is this clear? So 180 time and what do you think is going to be the difference between this and this? Again, that is going to be 1 stroke. So that would be another 180, another 180, and so on. So what is 80? 180 into 4. What is it?
720.
Yeah. Clear?
Yes.
All right. Lovely. So let's go. So I stand corrected, not 360 into 4. My bad. So it's 180 into 4 for a 4-stroke engine. So 1 second. I hope the working is quite clear. Now let's move on to the second point. Now what I want to really talk about an IC engine, which is also very interesting. So it has components that rotate. Oops, I'm sorry. Yeah. So it has components that rotate, reciprocate, and a suitable mechanism to sustainably control and continue performing mechanical work as long as the fuel and air are combusted. So there is a reason why I have emboldened a few words. What do you think is the reason? Chemical engine energy is emboldened, air fuel is emboldened, mechanical work, rotate, reciprocate, mechanism, control, cycle. Why do you think I've emboldened these words? Anybody?
They are important.
Of course, I mean, that's the truth. So the idea is all these words are important keywords. So rotation, I hope you guys can understand what rotation is, right? So you have this crankshaft which is rotating, and reciprocation is basically what your piston head is doing. It is reciprocating, and this is a suitable mechanism. And what is a mechanism and other things, they have to be formally explained. So I'll get back to the definition of what a mechanism is in the future in the sense the next few minutes. And the most important thing word here is sustainably control and continue performing mechanical work as long as the fuel is combusted. So essentially the point I'm trying to get across is an engine should be capable of producing power sustainably, and you should have the leverage to control it. So an engine isn't something that is just capable of converting one form of energy to the other. So you have a different name for it. It's called a transducer. Yeah. So okay. So the final answer was 180. Yes. So the answer is 180. Yes. Yeah. So an engine is essentially a machine that is not only able to convert one form of energy to the other. It is also having some components, some of which rotate, some of which reciprocate, and you have some suitable mechanism that can control the engine, and it should sustainably keep producing or keep performing that mechanical work as long as you have some fuel supply or you have some temperature gradient or whatever is necessary for the engine to run. Okay, so these are all keywords. So what makes an IC engine an IC engine is because is that the combustion takes place inside the mechanism. So the combustion is essentially inside the mechanism without requiring a separate chamber. So obviously, if I'm able to name this as an internal combustion engine, there has got to be some situations where you also have external combustion engines. Right? That's obvious, isn't it? Combustion engines. So can anyone think of an example of external combustion engine?
Jet engines.
Lovely. Yes, jet engines are. Jet engines are. Not all jet engines, but a few jet engines certainly.
So
And
ramjet,
whatever.
ramjet.
Yeah. So yes. You also have other engines. For not what you see in a power plant. So in a power plant is pretty much the same name that you use even in jet engine, to be honest. So here in jet engines, you follow a thermodynamic cycle called as a gas turbine cycle, which we'll not get into because our focus is on a different thermodynamic cycle, which I'll introduce in the future. So power plants, you have a boiler here. You have, you have a boiler, let's say, filled with water. Hopefully it is treated water, and then you have a heating coil, or you're basically, let's say, you're not, or you're just burning coal or air fuel mixture, and the water gets hot, and then it becomes steam, and then you heat it as it goes to your turbine, and turbine is basically a turbo machine. Turbo machines are essentially machines that are capable of converting thermal energy to mechanical work, or vice versa, mechanical work to some other form of mechanical that take in energy to perform mechanical work. And you have a nozzle here. It is going to blow the hot steam, and that is going to drive your turbine. So all of these things are not within the same mechanism. They are not contained within the same thing. So you have combustion, yes. This is an engine in a way, yes, because it is able to convert the thermal energy of steam to mechanical work. But then the issue is that they are not placed in the same chamber. Therefore, this requires a separate chamber. You have something called as a boiler room. So this becomes an example of an external combustion engine. Is this clear? So the reason it is called an internal combustion engine is that you see that this is the entirety of the mechanism. This is the entirety of the mechanism. And all the combustion and other thing takes place within the mechanism. That is what makes it an internal combustion engine. Is this clear?
Yes, sir.
All right, lovely. All right. So let's move to the next thing. So the engine follows a thermodynamic cycle. Now this is the nice part. So the engine follows a thermodynamic cycle, and like everything else in the universe, it is governed by the laws of thermodynamics. So can anyone tell me what the 3 laws of thermodynamics are? They have 3 laws, or you have 4 laws? Let us ask that question. How many laws of thermodynamics do you guys know? How many laws are there? How many laws of thermodynamics do we know? Please
3, right?
unmute.
3.
Yeah.
3.
Okay, 3 laws. Lovely. You have 3 laws. Yeah, I'm sorry, I was not able to hear.
No, there's
Yeah. Okay. Some say 4 laws. Fine. So, okay. So actually the answer is there are 4 laws. Okay. You have the 0th law, the first, second, and third. So can anyone tell me what the 0th law is? Yeah, please. I want this session to be quite interactive, man. Obviously, most of you would have learned this. So there are 4 laws of thermodynamics. The first law was later added. The 0th law was the last to be formulated, even though it's probably the first law that we have implicitly used in thermodynamics. So what is the zeroth law? Anybody, please? Okay. The third law of thermodynamics is derived from the first and second law. It gives no new information as far as I know. Yeah, I mean, you have people who do tell you that, but chemists actually take the chemists and engineers, at least they take third law to be sacrosanct. Of course, physicists, we try to reduce these things. So what is the zeroth law? Tell me.
Sir, if two systems are in thermal equilibrium with one system, then both the systems are in thermal equilibrium.
Exactly. So it is like your Euclid's equivalency, postulate, isn't it? If A equal to B and B equal to C, then A equal to C. Yes. So if A and B are in thermal equilibrium, B and C are in thermal equilibrium, implies A and C are in thermal equilibrium. Fine. That's the first law. That's the zeroth law. What is the first law? Which is probably the most important law in all of physics, I'd say. What is the first law?
Energy can be converted from one form to another, but can't be created or destroyed.
Lovely. Energy can neither be created or destroyed, but can be converted from one form to the other. And that's exactly what we see here. So anyone, can anyone tell me what the second law is? Second law, please. Anybody? You can give me a textbook definition. Yeah, go on.
There are two statements, but effectively
Yes.
what we can get is
Yeah.
there is no engine that has 100% efficiency, and
Perfect.
there can't be any engine that can spontaneously transfer
Yeah.
heat from low temperature to high
Perfect.
temperature.
Absolutely nailed it. So that is the
Entropy always increases.
yes, very good. Entropy always increases. Yes. So all these are perfect statements. Okay. So I'm glad that a lot of you people know. So that's the second law. And what's the third law? At least the chemistry people should tell me. Or if you have done 12th standard chemistry or 11th standard chemistry, you should know what it is. What is the third law? Come on, quick. Motion ceases to exist as T tends to
Zero.
At absolute zero temperature.
yeah. So entropy is zero.
Entropy is zero at absolute zero.
Exactly. So as Sagar said, obviously, if you have understood what entropy is in the physics context of things, and you understand what temperature is, you will be able to tell you that third law is just it can be derived from the first and second law. Anyways, notwithstanding that, let's move on. So an engine is of course going to follow a thermodynamic cycle, and it is going to obey the laws of thermodynamics. Or in other words, let's say you have you're able to develop an engine, and that engine is able to give you 100% efficiency. That is impossible. Okay. And if it is going to give you greater than 100%, that is impossible even from first law consideration. So 100% efficiency is impossible as per second law. Greater than 100% is ruled out by first law. And when we are talking about thermal equilibriums, thermal equilibria and other things, we are implicitly using the zeroth law. And because engine will cease to exist, or will not perform when the temperature tends to 0 Kelvin, it is also obeying your third law. Is this clear? So an engine is perfectly going to obey the laws of thermodynamics. Is this clear? Can we move ahead?
Yes.
Lovely. All right. Let's move to the next slide. Yeah. Okay. Yeah. Oops. 1 second. I think I'll have to erase these guys. All right. Let's move to the next slide. Yeah. So now we answered what is an IC engine. Now let's try to answer the question of what why have I chosen IC engine? Okay. So, and why have I chosen this topic among many others that are available to specifically study what mathematical modeling is. So the idea is mathematically modeling an IC engine is a great opportunity to appreciate complexity in real life. So I'd like to take you guys through a small Venn diagram that I've made here. So as you can see, it is composed of different colors, different shapes, and thing. I hope most of you understand what a Venn diagram is. Do all of you know what a Venn diagram is?
Yes, sir.
Lovely. Okay. So Venn diagram, this is the legend. So the white part is what we think mechanical engineering is all about. The black part is, of course, what we have not found. So basically in Venn diagrams, what is a universal set, right? Universal set is whatever set you're interested, a union with whatever is present in the universe. Much the same way. So what engineers and physicists have discovered in mechanical engineering is only so much. The black region is what is left to be discovered, and the union of these two will give you what is the universal set. Okay. All right. Now let's go to what each of these regions in mechanical engineering that physicists and engineers have found. So we'll start with the black circle in the center, because this is exactly where you guys will be working if you join this course. So the black circle, as you can see, intersects with greatly with different areas of engineering and stuff. So let's go through each of these things one by one. So the red region is basically thermodynamics and thermal engineering, which is one of the most important areas in all of mechanical engineering, right? So thermodynamics and thermal engineering. So by doing this project, we will cover some aspects of thermodynamics and thermal engineering, because we'll be using that heavily. And the yellow circle is basically mechanics of discrete particles. And because thermodynamics and mechanics are very closely related, so they will actually intersect in this place. But then I'm only talking about the yellow part here. So let me just shade this yellow part here, because that is just mechanics of discrete particles. I hope you guys understand what discrete particles are. Do you know what is a discrete particle? What is the difference between a discrete particle and a continuous media? Anybody?
Sir, I do not know.
Okay, solids. So generally, how do you approach mechanics of solids? Not solids, or let's say, mechanics of point-sized particles. You would have studied in your 11th standard, right? Point-sized particles. So if you use Newtonian mechanics and you can count the number of points, and you reduce a man to a point, or essentially a center of mass, COM. Yeah. So are you able to understand what discrete particles mechanics is all about? I mean, it's basically what you have learned in your 11th standard, the first half of 11th standard, where you just use Newton's laws and you convert everything to point-sized objects and you study. Is this clear?
Yes.
All right. So
Yes.
yeah. So you'll cover this part, and you have thermodynamics and thermal engineering covering a big chunk. And the interesting thing is, because thermodynamics, thermal engineering, and your your classical mechanics is going to intersect greatly, and it intersects in a region called mechanics of continuous media. And in fact, in thermodynamics, you guys would have studied ideal gas equation and many other things, right? You'll have used PV equal to nRT, these sort of equations. And gases are like fluids. Gases are fluids, so they overlap. And there is a reason why this has been shaded in orange color. Can anyone tell me why? Why do you think this has been shaded in orange color? Even though this entire ellipse is just about mechanics, a specific region has been shaded as orange color, particularly the region that intersects your thermodynamics and mechanics. What do you think is the reason? Come on, man. You guys would have played with pastels and colors, right? What? Yeah, anybody? What do you get when? Yeah.
When you mix these two colors, you get orange.
Lovely. Exactly. So that's the beauty of visually trying to understand. So red plus yellow is orange, and that is why you have this. And of course, we are not going to cover the entirety of fluid dynamics or solid mechanics. We'll only be covering a part of that. So this is shaded. Lovely. And you see these. Now we'll come to material science and metallurgy. So you'll also be. I'll qualitatively teach you some key concepts from material science and metallurgy. So that will also be covered. So You might think, where the hell does material science and metallurgy come into mathematically modeling this. I'll get to all of these questions shortly, but just travel with me for now, right? The thing is, this slide is basically going to tell you what you're going to learn and why have I chosen this system to study, right? Now, coming to the cyan part. Cyan is the blue. Okay, we'll come to the blue part. So another important area, this is the second important area in mechanical engineering, and this is the zeroth important area, which you've already covered in 11th and 12th. First is what you'll cover in your typical engineering. Second is what you'll also cover in your typical engineering in your second year. And the other region is where you'll be taught kinematics and dynamics of machinery, typically in your second and third year of engineering, right? And this is another important area of mechanical engineering. And we'll be not covering the entire thing, obviously, but we'll be using some key, I'll introduce some key concepts from kinematics, dynamics and design of machines. Because ultimately, the takeaway from the problem is you'll be learning to design an IC engine after having mathematically modeled it. All right, so this is covered, this is covered, this is covered, and there are some regions here which are cyan, right? So cyan is whatever you have already learned from different places. So we'll also be using your previous knowledge. And let's come to the most beautiful place, which is the magenta, and which is your center. And this is something that you'll only learn from Nakshatra. We'll be focusing a lot on this magenta. All right. So this is something that you'll only learn here at Nakshatra. Fine. So is the Venn diagram clear? Okay. So Swarupa has asked a question. Are rocket engines classified under IC engines? No, rocket engines are not exactly IC engines. And the reason why rocket engines are not exactly IC engines is because, that's a technical reason. The technical reason is because the outer atmosphere also does some work, okay, on the control volume of that system. Obviously, if you don't understand, you'll have to, attend this course. But no worries. But to answer your question, rocket engines are sadly not classified under IC engines. It is because if you assume your engine as your control volume, you also have outside forces, particularly in rocket. You'll have a rocket, or at least a rocket in planet Earth. Till it gets out of planet Earth, it cannot be considered as an IC engine. When it is outside planet Earth, you can say that it is semi IC engine. But then, to be honest, these classifications are just namesake. What is really interesting about classifying? What is really interesting about engines is not the classification. This is quite superficial, but it is something to do with the physics behind that. Okay, clear? So let's move to this thing. So most complex systems are at the intersection of several closely. So what makes a system a complex system? So complex system is essentially where you have great deals of intersection. That is what this whole Venn diagram is showing. And the reason why we have chosen this black circle is because it intersects greatly with a lot of places. And we'll be using tools from mathematics, physics, mechanical engineering, and computation. And we'll try to model an IC engine. So in the process of modeling the IC engine, we'll pick up some key concepts from the aforementioned fields. And ultimately, what we want to do is we want to develop and solve integral differential equations that describe the observables. So we'll be developing differential equations, and we'll try to solve those differential equations the way a physicist, engineer, and a mathematician will solve. And we'll actually see that while the results are quite the same, the approaches are pretty different, and that will culminate into a report. Clear? So let's move on to the next slide. Any questions up until now? Can I move ahead?
Yes, sir.
All right, lovely. Okay, now answering the most pertinent question out there. So the main question was, what is the whole point of talking about IC engines if IC engines are going to become obsolete thanks to your electric vehicles? That's a very valid question, right? So to answer that question, I want you guys to go read about, what are the components that make a refrigerator, an air conditioner, a generator, a water pump, a locomotive, and a propeller aircraft. Of course, there are many other examples, but these are some things that you guys would definitely have seen in your life. So what do you think is a common factor for a refrigerator, an air conditioner, a generator, a water pump, a locomotive, and a propeller aircraft? What do you think is common to all of these? Anybody? Are?
Heat is exchanged.
Okay, heat is exchanged, yes. But in the context of IC engine, or in the context of, why I think IC engines are relevant in this thing. What do you think is going to unite all of these guys? Any idea? At least not everybody, but at least a few of these components, if you know.
So the transfer of heat is used to provide
okay.
movement or like change in.
Okay, lovely. All right. So Abik Mishra has
change in dimensions or something.
Okay, Abik Mishra in the chat has absolutely nailed it. So generator is essentially an internal combustion. Generator will have an IC engine. Okay. So generator, I hope you guys have seen a generator like this Honda, or you would have seen a Kirloskar or something, where you have a diesel. This basically has an IC engine that will drive an alternator or a DC generator. So this has an IC engine, so this is relevant. And this is one of those rare instances or cases where you actually take a lower grade energy to convert it into a higher grade energy. So what do I mean by lower grade and higher grade? So higher grade energy are typically forms of energy that can offer greater efficiency when they are converted to mechanical work or any other form of energy. Whereas low grade energies are forms of energy that do not provide as much efficiency when you're going to convert. So can anyone give me an example of high grade energy?
Electricity.
Yeah, electricity. Correct. That is the reason why we are all fond of electric cars. Electricity is probably one of the best high grade forms of energy. Can someone give me a low grade energy?
Petrol, diesel.
Yeah. Anything else?
Sound.
Sound. Okay. Sound is basically pressure wave, but it is not. It's not a low grade energy by.
Steam engine. Steam engine.
Exactly. Steam engine. Yes. Perfect. Coal. Yes. In other words, steam engine and coal, they are like happily married. Okay. So I'll give you even lower grade forms of energy that people will definitely not touch in university. So when you're talking about nuclear fission, okay, controlled nuclear fission, that is a very low grade energy. Okay. Why is it a very low grade energy? Because in nuclear fission, you should be able to control it. If you don't control it, what do you get?
Bomb.
Yeah. Yeah. Okay. You get a Chernobyl-like disaster. Okay. So nuclear fusion, when you are trying to convert it, when you are going to control nuclear fission, the efficiencies are of the order of 5%. What do you think is going to be the order of efficiency for let's say a petrol engine? Anybody? Just give me a number, na? We'll see.
20% or 25%.
Very good. 20 to 25%. Very good. Typically not greater than 40%. Maximum possible, I'm saying. Okay? Less than equal to 40%. So this is like, even though it is low grade, it is not as low a grade as controlled nuclear fission. Are you able to understand? Are you able to follow?
Yes, sir.
Sir, sorry to interrupt. I have a question.
Please go ahead. Please go ahead.
Yeah. So we have this electric propulsion, right, in satellite. So can we consider those engines as low grade engines?
Those engines are low grade engines. You will have to actually
Like in terms of the amount of thrust produced or even the mass flow rate, which is
Yeah.
totally low,
Yeah.
is there like can we consider them?
I would say they are medium grade. They are not exactly low grade or high grade. The reason I'm saying they are medium grade is because in your electric, basically what you're talking about is called ionic propulsion, ionic or plasma propulsion. And plasma propulsion is medium grade, at least in the context of satellites. Why? Because there are many reasons that contribute to efficiency. What is efficiency, by the way? Anybody? What is eta or what is efficiency? It's a ratio, na? Give me what numerator make, what is there? What is in the denominator? What is efficiency?
Input.
Yes.
Output by input
Yeah.
generator.
That's all. Output by input of some form. So typically when you are talking about, let's say, an ionic propulsion engine, so the output is basically the amount of thrust. And the input is basically thrust into velocity. That is going to be the power output. Thrust is a force, okay? Force into velocity is power. So power output divided by power input. What do you think is going to be the power input for an ionic propulsion? So in ionic propulsion, what is going to happen is you're going to heat a coil. Okay.
Yeah, exactly.
And so you get thermionic emission.
From that, through the exhaust nozzle, we'll be getting
exactly. So
but still
yes.
the amount of the mass flow rate is too low because of the mass of the ions that have been produced, and also
Yes.
the thrust delivered will be in micronewtons, right?
Yes, micronewtons. Yes. So
for basic maneuvers of satellites and all, we can say
that
it
is more than enough.
It is capable, but in terms of like by considering all the cryogenics, liquid solids, and all the hypergolic propellant engine,
yes.
can
So
as low grade.
Yeah, you can call it a low grade. Yes, if you're going to consider it as a whole. So there are different types of efficiency. Okay, one is called stage efficiency, and one is called overall efficiency. Overall efficiency of a thermionic emission is garbage. Okay, but stage-wise efficiency you can do something with it. Because to be honest, right, even in your thermionic emission and other things, when you're talking about a satellite, okay, it will have solar panels. Yes. And a lot of the heat that is going to a lot of heat that will be used in the thermionic emission is basically from whatever electrical energy is being absorbed by the solar panels. So when you're going to talk about an overall efficiency, you'll also have to talk about the efficiency of your solar panels and other things. But a stage-wise efficiency, you can just talk about, because for this stage, this is basically like free energy, because solar power, all you have to have is just your solar panel, and it is going to continuously generate. You're not performing nuclear fusion in the sun. Are you able to understand? So a stage-wise efficiency, thermionic emission, and the subsequent thrust and other things, that will make it into a middle grade energy. But if you are going to talk about an overall efficiency, yes, it will be garbage. Does that answer your question?
In case if we are able, like if we are constructing a proper ion thruster engine, so taking all the sustainable goals and all, in case of keeping overall efficiency aside, because of the mass flow rate and the amount of thrust produced, if we focus on stage-wise efficiency, can we build a sufficient, like a sustainable ion propulsion engine?
Yes, but the problem is, let me. What do you think is the solar constant? And do you know what is the solar constant?
Yes, like the amount of sunlight we'll be receiving per unit area.
Perfectly correct. Yes, so it is around 1.5 kilowatt. Okay. And what do you think is the typical efficiency of a solar panel?
Around 22 or even less than that.
Yeah, it is very less. Okay, typically, 20 is like if you have a high grade silicon wafer, and you have a very high this thing. But sustainably speaking, you cannot achieve more than 10% at best. Okay, so 10% of 1.4 kilowatt, and then you want to create an ionic thing, that is not going to work out. And one of the reasons, I'll tell you why. Okay, so we know that the universe is, we know that Earth is undergoing global warming, right? So you can't escape that. And ultimately, most of you would have learned what a Carnot efficiency is. What is Carnot efficiency? 1 minus T by some T. T sink by T source. Are yes or no?
Yes, sir.
Yeah,
Yes.
1 minus T sink by T source. So the problem is the T sink is actually increasing because of global warming. So even the maximum possible efficiency thermodynamically that you can get is going to be on the going to continuously reduce because of global warming. So it is not a very good sight, and that is why in physics we have a theory. It's called the heat death of the universe. That is when the universe will attain a system of will become a system of maximum entropy, and you will not have any available energy of heat to do useful work. You'll just have heat that is which is like the lowest for grade of heat energy available. So yeah, so the idea, I mean, if you are ambitious, if you want to do that, you can do it probably at a small scale. But if you want to scale up your engine to sustainably build an engine that can just based on thermionic emission and other things, it is not going to work out. Sadly, for the reasons that have already been discussed. Is this clear? Any other questions?
Yes, sir. It's clear.
Lovely. Okay, so yeah. Sagar has please check the chats as well. Sagar has given a wonderful example. So glycolysis. So glycolysis process in cells, which is completely enzyme catalyzed. It itself has an efficiency of 37 to I'm sorry. Let's go to the previous slide. Yeah. So glycolysis has very good efficiency, around 37 to 40%. And to be honest, chemical energy is like a middle grade or a low grade energy only. You don't exactly get a high grade. Yeah. Anyways, who was asking a question? Yeah, go on.
Sir, if efficiency lies like generally is below 50%.
Yeah.
So whatever we had in the textbook of fuel cells having efficiency more than 70%, is that true or still in research?
No. Fuel cells are very good. Okay. Again, the problem with fuel cells, okay, is that there's a problem with scaling stuff. Okay. So there's a problem with scaling stuff. So even to be honest, nuclear fission, if you don't control it, nuclear fission is like 100% efficient process. Almost 100%. Okay. The problem is you'll have to control it. Okay. And controlling nuclear fusion is going to reduce the efficiency drastically. So fuel cells have a better control. You can control whatever energy that you get from fuel cells more sustainably than what you can control from, let's say, your IC engine. And the energy losses of IC engines and what actually takes away the energy, I'll actually teach you. I'll actually present to you shortly. Okay. So fuel cells, yes, fuel cells are very good, and and fuel cells work very well in places where a lot of forces are absent. So when you're in outer space, for example, I think the astronaut whatever they are wearing, their suits, astronaut suits, and many other electrical and electronic paraphernalia that the suits have, they are using fuel cells to power. Okay, so fuel cells are very good, but the problem is it's about scaling. Fine. Is this clear, all of you? Can I go ahead?
Is that why?
Sir, I have one doubt.
Yeah, go on.
Sir, what's the maximum efficiency achieved for commercial solar panels?
I have to check it, man. Really, I don't know. And you'll have to have an international body actually certifying it. So I can claim that my solar panel is fantastically efficient, but I'll have to have a certification from an international body to. So I doubt if people have actually gotten their things certified, but I have not heard of solar panels being more than 30% efficient. I've never come across that.
So, sir, in commercial use?
Okay, commercial use, I don't know, man. Commercial, you can't get greater than 15%. So I've actually worked in a solar thing also before this. I've seen a freshly or a newly installed thing will not be greater than 15%. And of course, if you plot this, this is actually quite an interesting thing in itself. So this is lifespan in log scale, and you have efficiency here. So it will actually be on the decline. Okay. It will follow a curve like this. Of course, there will be a lot of noise here. Why do you think there will be a lot of noise here? So solar panels will be most efficient when the sun is overhead directly. Okay. So even though it's in log scale, on a day you'll have 12 p.m. 12 noon always happening. So that is when momentarily the efficiency will shoot up. That is what comes out to be this sort of noisy thing. Anyways, we are going very, very off topic, but of course, a lot of these subjects are fascinating in their own right. Okay, is this clear, guys? Can I go ahead?
Yes, sir.
All right. Let's get to the thing. Yeah. So Abik Mishra has perfectly nailed it. So generator has an IC engine. Okay. Air conditioner and refrigerator have what we call compressors, which are basically like opposite of IC engines in a way, compressors. Okay. Even your water pump has a reciprocating. This is an example of a reciprocating water pump. Rotating. Okay. And air conditioners and small refrigerators make use of reciprocating compressors. Okay. And locomotives, as you probably know, your standard diesel electric locomotives are composed of what we call V12 engines. So this is one cylinder, this is one cylinder. They are in a V type of fashion. If you make the diesel electric locomotive naked, you'll see that there are 6 rows of these sort of V12 engines, and all the V's are essentially IC engines. And propeller aircraft, the one I've shown is a World War 1 or 2 propeller aircraft. And before the advent of gas turbine jet engines, you had propeller aircraft. So you'll have a main shaft here. This will be attached to your propeller fan, and you'll have engines. Each of them, you'll at least have 4 engines in a 4-stroke. So if one engine is in 1 stroke, the other engine will be in a power stroke. So it'll keep your propeller always rotating. Okay. So the point I'm trying to get across is IC engines are relevant even with the advent of electric vehicles, because IC engines and related problems are finding use in many appliances and many other places. Okay. Can I go ahead? Hello.
Sir.
All right, lovely. So let's go ahead. Just a minute. Let's go ahead. Okay. So I'm more of a visual learner, and I'm pretty sure most of you are as well. So for people who are not able to visualize, this is your standard slider crank mechanism. Okay. And this is what your IC engine is entirely based on. And this is called as a 4-bar mechanism. Okay. And one of the reasons why we are studying IC engines, or typically the dynamics of such simple mechanisms, is because you can ultimately reduce any complicated mechanism to a reciprocating and a rotating part. And this is not something that is new to you guys. Reciprocating and rotation. Why? So when you studied rotational mechanics, okay, or when you study the mechanics of complex objects, so you will always fixate on 2 things. So you'll study the translation from the center of mass point of view, isn't it? So you'll reduce the entire extended body to a center of mass. Are yes or no? And you'll study its trajectory or dynamics, and from the center of mass as a point, you will try to understand what is the rotation. So any complicated motion can be broken down into rotations and translations. Yes.
Yes, sir.
Yeah. So much the same way, any complicated mechanism can be broken down into rotating and reciprocating parts, and particularly they can be reduced to your 4-bar chain or your slider crank. They actually speaking, these two mechanisms are equivalent, and maybe in subsequent lectures I'll show you how they are equivalent. But for the moment, you just believe what I'm trying to say. So the idea is one more reason why we are interested in studying, say, IC engines or reciprocate slider crank mechanism or 4-bar chain is because many complicated mechanisms in the future that you'll come across can also be mathematically reduced to these mechanisms. So that is another incentive as to why we are interested in studying. And there is a third reason also. So remember when I talked about a steam turbine being a external combustion engine, I mentioned the word turbo machine. Yeah. So generally, mechanical engineering, you have two different types of engines. Ones that use turbo machine, ones that use this guy. Ones that use turbo machines are ridiculously complicated. Okay. And you have so many areas of open areas of research. And I can't obviously, give you an exposure of hardcore turbo machinery right now. So I took the easier way out, which is equally complicated in a way, but something that can actually be done within a limited time frame. This is your slider crank. So this is the third reason as to why we are interested in studying these systems as opposed to turbo machines. Turbo machines are ridiculously complicated for a number of reasons if you want to holistically understand. Otherwise, if you want a simplified analysis, we can have a session on that, but that is not going to take anywhere. Okay, can we move to the next slide?
Yes.
Lovely. Okay, so this is your project structure. So this is how it is going to run. I'm planning for 15 lectures, split into 5 weeks. And in the 6th week, you'll have a LaTeX and a Python complementary course. In the 7th and 8th week, you'll have a project where we'll be presenting, your final presentations, and you'll be writing your report. So the first week is just about, introducing some key ideas of mathematical modeling. I might be able to skip this if you guys already know your 11th and 12th standard mathematics well. So do you guys know your 11th and 12th standard mathematics well? Because first week is about that, and a few advanced concepts which I can cover within a session or two. That is not going to happen. That is not going to be a problem, because I realize that most of you are from COVID batch, if I'm correct. How many of you are from COVID batch? Can you just, yeah. Do you guys want the first week where I cover, some basic mathematics, if need be? Please let me know in the chat. Of course, this, if need be, we can do that. So the second, in the second week, we'll be talking about our problem description. Okay, what are the components of IC engine? It's working. What are the key observables and how they are done experimentally? Then we'll have a rapid review of thermodynamics, and then we'll have a rapid review of Newtonian mechanics. And in the third week onwards, we'll have the main project. So we'll start to model an IC engine. First, we'll perform an ideal IC engine. Then we'll compare the model with experimental data, and we'll understand, there are some observed discrepancies, and we'll introduce the first correction, which is called the isentropy correction. And we'll talk about what is dry and wet friction and how we are going to model wet friction as a Cauchy flow. So modeling wet friction is from fluid mechanics. So we'll delve into fluid mechanics, and then we'll talk about heat transfer, convective heat transfer. So we'll also be talking about heat transfer. Then we'll try to model a real engine. Then we'll talk about role of oscillating stresses on elastic members and ideas of fatigue and creep that we'll deal with qualitatively. Fatigue and creep are very important concepts when it comes to designing stuff. And these are from metallurgy and material science. So then we'll run into mathematical, methods of solving it. So this is applied math here on. So we'll try to have semi-analytical solution. We'll do something called order of magnitude analysis. Then we'll understand the need for numerical simulation. Then I'll teach you how do you numerically simulate stuff. So that is theory of computation. Then finally, we'll tie up loose ends. I'll teach you what is balancing of engine in a qualitative way. Then any other topics if permits. So this will be your overall structure of the course. Okay. So you'll be getting this. I'll be sending you a copy of this if at all you want to keep check this as you please. So with this, I end the first part of the presentation, where I've answered, I think, 5 of the 6 questions that I've asked. So let's go on to the next part of the presentation. Just give me a minute. Any questions up until now?
Sir.
Yeah.
I still didn't get why ICs are relevant.
Okay, who's this?
Sir, Deepak Khatare.
Yeah, so IC engines are relevant for a number of reasons. So one of the reasons is that even if you want to, let's say, talk about electric vehicles and hybrid vehicles, what is actually going to convert one form of energy, which is your chemical energy in the fuel, to electrical energy that is going to drive your induction motor or servo motor, is going to be through an IC engine. You cannot have any other way of converting it, unless of course you say you're going to opt for a completely solar powered vehicle. And solar powered vehicles are of course they are not scalable exactly. So IC engines are relevant even in that context. So you need a local power plant that is able to convert your chemical energy, or in the form of reservoirs, to electrical energy. And you can argue that you can replace that local power plant with batteries. But then the battery, you have a lot of research and you have a lot of issues surrounding batteries as well. So the natural way of going from let's say completely fossil fuel dependent automobile that we have today to electric vehicle will be through a transition where you have hybrid vehicles. And most of us have probably come across hybrid vehicles ourselves. So as long as there is going to be a demand for hybrid vehicles, IC engines will always play a role. And I'll go one step further and tell you that when it comes to let's say powering huge machines or huge forms of transport like ships, you have a diesel electric power plant only in your ship. So where do you think most of the cargo in the world is like being transferred? It is through ships. So obviously IC engines are relevant even in that case. And apart from that, whatever you are going to study in this course, or whatever you are going to use in this project knowledge, that is going to come helpful. That is going to be helpful when it comes to modeling other closely related stuff like compressors, for example, pumps, reciprocating compressors and reciprocating pumps. So it is relevant in these many different ways. Does that answer your question, Deepak?
Yes, sir.
All right, lovely. Okay, so let's go to the next part of the presentation, where I'll briefly discuss what that problem is. So that will be very short and sweet. And the last thing is what I initially talked about, mathematical modeling, right? And that will probably be your first exercise. So let's start that. 1 second. Let me just open up my presentation. Any other questions? Please keep them coming. Okay, I want this to be as interactive a session as possible, so that you guys really understand what is going on. Okay, let me just share my screen now. Okay, lovely. Someone has asked a question. What is it? Okay, so Sagar is done. Lovely. Sagar. So Sagar has posted the link also. Just go through that link if you're interested. Okay, so yeah, this is your and maybe I can share this file. Is it visible, all of you?
Yes, Google.
Yes.
Okay, lovely, fine. So we'll do this now. So so what is the outline? As we had already seen, IC engines work on the principle of converting chemical energy to mechanical work. Combusting air fuel mixture, all of these things have already been seen. So this is a schematic of an IC engine, and maybe I'll finish the nomenclature part right away because it is interesting. It is important if at all we are going to do that. So in the future classes, I can save up some time. So this is called a crank. This is called a crank shaft. This is called a flywheel. And this is going to rotate, obviously, in the anti-clockwise sense or a clockwise sense. Here I've shown it to be in clockwise sense. And this is your piston head. And this is your cylinder. And piston set is going to obviously oscillate, back and forth this way. And there is a tiny gap that you can see that the piston head is going to have with your cylinder. This is a tiny crevice of sorts. Just keep this in mind. And this is called a piston ring. And the rest is the rest of the quantities that I've shown here are just for mathematically modeling the system. So phi is just the instantaneous angle that this crankshaft is going to make. Omega is its angular velocity. I is the moment of inertia. L is length of the connecting rod. Theta is the instantaneous angle that the connecting rod is going to make with the horizontal. P is the pressure of the gases, expanding hot gases. H is the height of the piston. Mu is, what do you think is mu? Anybody? Come on, what do you think is mu here? Why have I shown it like this? What is mu? Open up. Come on, man. You guys would have studied this, man. Yeah, someone has answered. Who has answered? Yeah, exactly. Abik. Right. So it's coefficient of friction. Okay. And here is where your lubricating oil will be there. Okay. So the small crevice will have your lubricating oil. Why do you think you need lubrication?
To increase efficiency.
Exactly. But in what way? I mean, physically, what does lubrication do?
Reduce
There
friction.
should be no loss of heat.
Exactly. So you will lubricants are used for, there are two key purposes. One is to, of course, reduce metal to metal contact and reduce abrasion, wear, and friction. Okay. And the other is you have hot gases here. What do you think hot gas will do when it comes in contact with a metallic surface? It is going to transfer heat, and your piston head is going to become very hot, isn't it? Yes or no? Yeah. Have you touched? Let's say you're in a bike. Obviously, most of you would have ridden, around bikes. So you have your engine here, which is like a two-stroke V-wala engine. Have you guys touched that engine when it is in operation? Anybody? Arey, open up, man. Please answer.
Yes.
Yeah. What has happened?
It was hot.
Exactly. It is very hot. Okay. So the reason it's very hot is because of the hot expanding gases and the fact that the hot expanding gases come in contact with the cylinder as well as the piston head, and they transfer their heat. Okay. So the lubricant is also used to carry away the excess heat. Carry away excess heat. Because if the heat is not carried away, what do you think is going to happen? The engine will
cease.
Exactly. Okay. So what is engine seizure? You just go check. Okay. I'll not spend time. So for some of the, I'll just be giving keywords now and then. So go through these things. Okay. So this is essentially your this is a nomenclature of a simple IC engine. Okay. And the rest of the quantities that I've shown here are just to mathematically model it, as has been already discussed. So for when you're trying to understand what the losses of the system is going to be, so there are so many losses that so in the first step of modeling your IC engine is going to be when you consider there are no losses and everything is going to be ideal. No losses plus ideal. Okay. So ideal in every way. So even the air fuel hot expanding gas, you will be modeling it as ideal gas. Okay. And there are no friction. So mu is equal to 0. And there is no viscosity. So your eta is equal to 0. Okay. And heat is perfectly being transferred. So, all of these constants are useless. So the first step of modeling your engine is going to be an ideal IC engine. Okay. And the ideal IC engine should follow a thermodynamic cycle. So let's get to what thermodynamic cycle does it follow. Okay. So this is the ideal thermodynamic cycle that your IC engine should follow. So what is that ideal cycle? So the IC, this is called as a diesel cycle. Okay. And the left-hand plot is what gives you the pressure volume diagram of the air fuel mixture in an ideal IC engine. Okay. So what are the what is it composed of? It is composed of two different things. Okay, two different processes. These processes are reversible adiabatic, or what fancy engineers call isentropic. Okay. What is reversible adiabatic or isentropic? Anybody? What is adiabatic process? Okay, maybe I think
there is no heat energy exchange involved in the process.
Exactly. Yeah. So
or
there is
the
no
entropy remains constant in the process.
Exactly. So that is why it's called isentropic or reversible adiabatic. Okay. So anyways, we'll have a rapid revision of thermodynamics also as a part of this course, because I understand that not all of you are familiar with a lot of concepts here. No worries, we'll get to that. But the whole idea, I'll just briefly discuss what this problem is about. So this is the cycle that we expect the engine to follow, but this is the sort of cycle that we get. Okay. So this is going to be like PV power gamma equal to constant, which is a very nice thing. But these two things are not going to have that. Okay. These are very random shapes. And what do you think is going to be the area enclosed in this graph going to give you? Anybody? Yeah. Tell me. No worries, money. Yeah. Yeah. Work done, isn't it? And work done is going to, work done per cycle. Yes, that's a very important thing. So work done per cycle. And work done per cycle is the numerator in your efficiency equation, isn't it? Yes or no? So the denominator is the heat supplied, QS. So the area enclosed in this curve is going to determine how big of an efficiency you're going to have, isn't it? Because it's the numerator. Yes. So you see that this area is actually reduced to this area. So what do you think is going to happen in a real engine? Will the efficiency increase or decrease? At least from the visual thing. Kya hoga? What do you think?
Decrease.
Decrease. Why? Because the area is small. And this is what you have experimentally observed. So the whole idea of this project is to mathematically understand what is the relation between the thermodynamic cycles that you see here with the dynamics of the piston head and the crankshaft. When it is put in an environment where there is friction, where there is viscosity in the lubricating oil, where you have you have other forms of losses, like there is a constant heat transfer loss because of the lubricating oil. Friction is going to take away some energy, and there is another loss which is quite which is not very much pronounced in this engine, but will be important in many other engines, what we call as elastic member loss. So you understand that your connecting rod and crankshaft are elastic members, right? So do you understand what is elastic member? Yeah. What is an elastic member? You apply stress, what will happen to the elastic member? It is going to expand. And when the stresses are in the opposite direction, it will get compressed. So in this process, you have continuous cycles of stress versus time. You have continuous cycles of cycles of this being pulled both ways and pushed both ways. So some amount of energy will go away in expanding and contracting the elastic members. So these losses will also play a role. So the ultimately, the real IC engine will have so many losses, and from first estimate, where we assume that the engine is going to be an ideal engine, we'll try to mathematically derive an equation. So the equation will be like pressure. Let me give you a simple example. So pressure of the gases into the area is going to be the force, right? Pressure into area, it will be the force, which is going to be equal to mass of the piston times d square x by dt square. Okay. And this d square x by your x is going to be related to your omega, and omega will be related to your power output, which is just half I omega square. Okay. I mean, I'll teach you all of these things. The idea is you want to relate a thermodynamic quantity like pressure to a mechanical quantity like omega. Okay. And what is going to be the functional form is what the entire project is about. So we hope that by mathematically modeling the system from an ideal system all the way to a real system, considering all the losses, we will be able to establish the reason as to why this guy becomes this guy. Okay, that's the whole idea. Is this clear? That's the whole problem. Any questions?
No, sir.
All right. Okay, I think it's already 1.5 hours, right? So maybe I'll take up the example of the mathematical modeling thing some other time. Or if you guys are interested, it'll take probably 10-15 minutes more. So I'll give you a taste of how a physicist, a mathematician, and an engineer will do. So if you guys are interested, I'll do that, or maybe we can have it some other time. It's choice is up to you. How many of you would like 10 minutes more of this session to go on, or how many of you think we'll save up the mathematical modeling example for some other day? Choice is yours. Please put it in the chat. How many of you want it now? If I can continue, or if I can have it some other time. Okay, 2 people have put now. 3 people have put now. Lovely. Okay, 4 people have put now. I need at least more than 50%, guys. So otherwise I'm not moving. Sadly, it is democratic here. Anyone else, please? I mean, make use of the chat box, or if I can continue, I'll continue. No worries. So Sagar, what do you reckon? Do you think I can continue it for just 10 more minutes, or? Rakesh?
Yeah. I don't know, but actually,
yeah,
what
I think
feel
this is already, because it's already 90 minutes. Yeah, it's more than 1 hour. Okay, I'll maybe what I'll do is I'll put it in I'll formally write it down. I'll give a good solution. I'll put it into a PDF and I'll send it to you, and you can share it with the students. And if they have any questions, we can have a separate session, maybe tomorrow or day after, whatever, if they are interested. Okay, that can also be done, arranged.
Okay, fine.
Is that done? Okay, thank you, all of you. I'm sorry, I mean, I see that a lot of people are very interested. I'm overjoyed, but let's not get too ahead of ourselves. It's already 9 minutes, so no worries. I'll put it in LaTeX, or I'll neatly write these things down. I'll give you an example of one problem. I'll go through it in 3 different ways: how an engineer will do, how a physicist will do, and how a mathematician or an applied math person will do. And I'll give you one problem which is like a homework. So I'll give you some time. So yeah, save this enthusiasm for the project. Please register if you are interested. And if you have any questions or comments now, I'm open. Please open up. If you have any questions or comments or suggestions that you'd like me to address. If you're interested, if you really think you learned something at the end of this 90 minutes, I'll be very happy. So any questions or comments? Anybody? Sagar has put it there. Yeah, okay. Swarupa
Okay,
has asked.
so
Yeah.
I have put the registration link now.
Yes.
So if you're interested, you can join.
Yes, Swarupa. So we can ultimately we'll be doing it on MATLAB, and if you're interested in MATLAB Simulink, you can do it. Or I prefer using standard C, C++, or if you have Python, you can use Python to simulate this. Ultimately, we'll be numerically solving differential equations. We'll first set up that differential equation. We'll try to find out some theoretical analytical result based on reasonable assumption by ignoring some terms or by hypothesizing a function, and we'll also be solving it numerically. And finally, we'll compare the theoretical result with the numerical result, and that will be the end of the project. Is that clear, Swarupa? You can use MATLAB if you want, or you can use Python or C++ or whatever programming language that you are interested in. Is this clear? All right, lovely. Okay, then thank you, students. Thanks for joining. And by the way, just one more thing. So if you are you guys comfortable with my language? So if you want something in your local tongue, I can speak 4 languages well. I can understand 6 languages really well. So if you want something to be taught in your native tongue, or maybe if you have some questions, you can ask me in your native tongue. So I know Tamil, that is my mother tongue. I know English, I know Kannada, I know Malayalam, I know Telugu, and of course English, Hindi, yeah, Kannada, Tamil, Telugu, and yeah. So pretty much the South Indian languages and Hindi as well. So and English, because which is lingua franca. So you can make use of that as well. Okay. All right then. Thank you for joining today. If you have any comments, questions, or things, you can contact me at this number. Let me just put it in the chat box. So please do register for this course if you're interested, and see you hopefully in a week's time, where we'll officially start the course. Thank you.
We have a WhatsApp group dedicated to the discussions of IC engines, which is free for everybody to join. So I'll put the link of WhatsApp group here in the chat box. So you can join the WhatsApp group, and we'll be discussing about IC engines and other mechanical engineering stuff in this group. Okay.
So that is my number. I've just put my number in the chat box. Please check it. If you have any questions, comments, or contact, you can always reach out to me. Thank you for patiently putting up with me. It has been a lot of monologue, but I definitely enjoyed the interaction that I got. So thank you for joining today. And hopefully I believe that you guys learned something at the end of 90 minutes. And if you're interested, please do reach out to the course. Thank you. Cheers. Bye.
Thank you, Ukul. Thank you for
Thank you, Sagar. Thank you, Sitara, for organizing. Thank you, Sagar, for staying through this entire meeting. And thank you, students, for joining. Thank you. Cheers.